If you are holding a cup of coffee right now, or simply sitting in a chair reading a screen, it feels like you have a pretty good handle on what reality is made of. In the last episode, we mapped out the standard model of particle physics, the ultimate cheat sheet of the universe. We discovered that everything you can see, touch, and interact with isn't made of hard little billiard balls, but is instead a collection of stable ripples vibrating inside a handful of underlying quantum fields. It is an incredibly beautiful, mathematically precise picture that has been tested to better than 1 part in a billion. You look at that framework, and it is tempting to think that human beings have basically solved the cosmic puzzle. But physicists are harboring a terrifying secret. All of that, every single electron field excitation that makes up your body, every photon field ripple that lets you see light, and every quark field that binds atomic nuclei together, is just a tiny fraction of what is actually out there. Everything we have ever detected in every microscope, telescope, and particle accelerator in human history accounts for a mere 5% of the universe. The other 95% is entirely missing from our equations. The standard model isn't a complete map of reality. It is just a map of the foam floating on top of a massive, dark, and completely unmapped quantum ocean. If particles are just local excitations of fields, then the vast majority of the universe must be filled with phantom fields, invisible mediums that are humming with energy right now, passing straight through you, completely undetected. This video is the step-by-step breakdown of how physics backed itself into this new shadowy corner, and how we are using quantum field theory to hunt down the missing 95% of existence. To understand how we know these phantom fields exist, we have to look at how the universe moves, because something is pulling on the scales. Back in the 20th century, astronomers started measuring how fast galaxies rotate, and the math immediately collapsed into nonsense. Think about a standard playground merry-go-round. If you spin it slowly, children can sit on the edge comfortably. If you spin it at a furious speed, the centrifugal force will overcome their grip and fling them off into the grass. A galaxy behaves the exact same way. The only thing keeping the stars on the outer edges of a galaxy from being flung out into the empty void of intergalactic space is the gravitational pull of the matter sitting inside that galaxy. But when scientists calculated the total mass of all the visible stars, gas clouds, and dust inside these rotating galaxies, they realized there wasn't anywhere near enough gravity to hold them together. Based on classical physics and Einstein's relativity, these galaxies are spinning so fast that they should have torn themselves apart billions of years ago. Yet they sit there perfectly stable, spinning tightly like clockwork. It is as if there is a massive invisible hand holding the outer edges of the galaxy together, providing a crushing gravitational grip that we cannot see. Physicists named this invisible glue dark matter, but labeling it didn't solve the mystery. For decades, people wondered if dark matter was just regular stuff that was hard to see: dead stars, rogue planets, or massive clouds of cold gas that didn't emit light. But our understanding of quantum fields completely rules that out. If dark matter were made of regular atoms, it would still block starlight passing through it. It would still bump into other gas clouds, and it would absorb and re-emit radiation. It would talk to the electromagnetic field. But dark matter doesn't interact with light at all. It is literally transparent. When you view this problem through the lens of quantum field theory, the answer becomes both elegant and unsettling. Dark matter isn't a collection of invisible space rocks drifting through an empty container. It must be a completely separate, independent layer of reality, a dark matter field that permeates the entire universe, sitting right on top of our own fields. So why can't we feel it? Why doesn't it show up in our labs? The answer comes down to a property called coupling strength. In the field picture for two fields, to notice each other, they have to be coupled, meaning they have to share an interaction rule that allows them to pass energy back and forth. Your hand can pick up a cup, because the electron field in your hand and the electron field in the cup are heavily coupled to the electromagnetic field, allowing a furious exchange of virtual photons at close range. That exchange is what creates the physical sensation of a solid boundary. But the dark matter field is entirely uncoupled from electromagnetism. It simply does not speak the language of photons. An excitation in the dark matter field can pass straight through the fields of your body, like a ghost passing through a brick wall, because there is no underlying field mechanism to push back against it. The only field it seems to care about is gravity. It possesses energy and momentum, which means it warps the fabric of space-time, leaving a massive gravitational footprint across galaxies while remaining completely silent to every other detector we have ever built. We are living in a universe where an entirely separate quantum world is overlaying our own, sharing the same space, humming with its own quiet energy, but completely cut off from our sight, because the two worlds refuse to talk to each other. If the dark matter field represents a massive weight pulling the universe together, the next phantom layer does the exact opposite, and it is tearing the universe apart. Back in the late 1990s, astronomers set out to measure how fast the expansion of the universe was slowing down. Everyone assumed that the collective gravitational pull of all the matter in the universe, both regular matter and dark matter, would act as a cosmic brake, gradually dragging the expansion to a halt. But when they measured the light from distant exploding stars, they found something that shocked the scientific community to its core. The expansion isn't slowing down at all. It is accelerating. Every single day, galaxies are flying away from each other faster than they were the day before. To explain this cosmic acceleration, physicists had to invoke a new kind of entity, dark energy. And just like dark matter, the true nature of dark energy only makes sense when you zoom all the way into the vacuum of space using quantum field theory. In classical physics, a vacuum is just empty space nothingness. It has zero energy. But as we established in the previous episode, quantum field theory proves that a vacuum is never truly empty. Even when you remove every single particle, the underlying quantum fields are still there, humming at their absolute lowest possible energy state. This baseline energy is called vacuum energy, or zero-point energy. Because this energy belongs to space itself, it exerts a unique kind of pressure. According to Einstein's general relativity, while normal mass and energy create attractive gravity that pulls things together, the uniform energy of a vacuum creates a powerful repulsive pressure. It pushes outward on the fabric of space-time. As the universe expands and creates more empty space, it also creates more vacuum energy, resulting in a relentless compounding outward push. This sounds like a beautiful, seamless synthesis of relativity and quantum mechanics. But when physicists actually tried to use quantum field theory to calculate exactly how much vacuum energy should exist in our universe, they ran into the single greatest disaster in the history of science. The calculation involves adding up the minimum baseline energies of every known quantum field in the standard model. When you run that math, the predicted value for the vacuum energy comes out to a number so colossally large that it defies human comprehension. It is roughly 10 to the 120 times larger than the amount of dark energy we actually observe in the real universe. That is a 1 followed by 120 zeros. Think about the scale of that error. If the theoretical calculation were correct, the repulsive force of empty space would be so violently intense that it would have ripped the universe apart in the first fraction of a microsecond after the Big Bang. Atoms would never have had the chance to form, stars would never have ignited, and the universe would be nothing but a sterile, hyper-expanded void. Yet you are sitting here, and the universe is expanding at a gentle, measured pace. This mismatch is known as the cosmological constant problem, and it is the ultimate crisis at the frontier of modern physics. It tells us that our equations are profoundly broken when it comes to understanding the energy of empty space. The quantum fields are humming with an energy we can calculate, but the universe is responding to a tiny fraction of it, meaning there is a massive piece of the puzzle. Perhaps a hidden mechanism that cancels out this infinite energy that we are completely blind to. But the mystery of these dark hidden layers doesn't just dictate how the universe expands on a cosmic canvas. It is the absolute singular reason we are even alive to look up at the night sky and ask questions about it in the first place. To truly grasp the gravity of the situation, we have to look past the passive drift of galaxies and analyze exactly what happens when you poke a quantum field hard enough to force it out of its quiet vacuum state and create matter from scratch. According to the mathematical equations that form the bedrock of quantum field theory, energy and matter share a relationship of perfect mirror-like symmetry. When you inject a massive concentration of localized energy into a quiet, undisturbed field to forge a ripple, a physical particle, the underlying physics demands that you can never, under any circumstances, create that particle alone. Every single time a regular particle of matter is born from a field excitation, an identical twin carrying the exact same mass, but an entirely opposite electric charge is created right alongside it. This is antimatter. If the field is pushed to create an electron, it must simultaneously create a positron. If a high-energy interaction rips a quark into existence, it must instantly balance the cosmic ledger by creating an antiquark. And the operational rules governing these subatomic twins are absolute, unforgiving, and violent. If a particle of regular matter and its corresponding antiparticle ever cross paths, they do not simply bounce off one another. They immediately undo each other's existence in an instantaneous process called annihilation. In a fraction of a second, their physical structures vanish completely, exploding in a flash of pure radiation and dissolving straight back into the underlying photon field as high-energy gamma rays. This deep fundamental symmetry is not just a neat theoretical trick baked into the abstract mathematics of the Standard Model. It is a physical reality that works with flawless, predictable precision inside our modern particle accelerators. Every single day, when engineers smash protons together at close to the speed of light inside the massive rings at CERN, our detectors record the aftermath. Without fail, every single collision creates matter and antimatter in perfectly equal 1-to-1 ratios. The symmetry holds true across every energy scale we can physically manifest. But when you take this flawless mathematical symmetry and try to apply it to the ultimate high-energy event, the beginning of time itself, it hits a terrifying, catastrophic paradox. In the earliest microscopic fractions of a second following the Big Bang, the universe was not filled with stars or planets. It was an unimaginably dense, hyper-concentrated, blindingly hot soup of pure raw energy. As this primordial furnace rapidly expanded and cooled, that raw energy began to condense into quantum field excitations, triggering the birth of the very first particles of matter in cosmic history. Because the laws of quantum field theory are perfectly symmetric, this transition should have been a perfectly balanced event. For every single particle of regular matter forged in the cooling fires of the early universe, an exact matching particle of antimatter must have been created alongside it. Think about what a universe dictated by that math would actually look like as it grew. As the cosmos continued its rapid expansion, those trillions upon trillions of freshly minted matter and antimatter particles would have been packed tightly together in a chaotic, colliding frenzy. Naturally, they would have bounced around, run into their opposing twins, and completely annihilated each other. Every single scrap of solid material, every quark, and every electron would have vaporized, converting instantly back into pure light. The universe would have effectively erased itself before it ever had a chance to begin leaving behind an empty, dark, and utterly sterile void populated by nothing but a uniform haze of wandering photons. Yet, look around you. The stars are burning in the night sky. Heavy galaxies are spinning through space. The rocky ground beneath your feet is completely solid. You exist, breathing and thinking. And as far as our most powerful telescopes can peer out to the furthest edges of the observable universe. Billions of light years away, every single structure we observe is made entirely of regular matter. There are no antimatter stars, no antimatter galaxies, and almost no natural antimatter to be found anywhere in the cosmos, except for the fleeting traces produced in extreme laboratory conditions or cosmic ray collisions. This absolute mismatch can mean only one thing: the Standard Model is missing a fundamental, monumental law of nature. Somewhere in the blinding chaos of the early universe, a subtle, hidden, and deeply profound asymmetry must have tipped the scales at a level our current equations cannot detect. As the primordial energy condensed, the universe could not have been perfectly fair. For every 1 billion particles of antimatter that were created, the underlying fields must have experienced a microscopic glitch, an unmapped preference that forced the creation of 1 billion and 1 particles of regular matter. It is an infinitesimally small discrepancy, a literal 1 in a billion error in the cosmic ledger. But that tiny asymmetric remainder was everything. When the expansion forced the great cosmic purge and the vast oceans of matter and antimatter violently annihilated into a sea of light, that microscopic 1 in a billion leftover fraction was the only thing that survived the meat grinder of the early universe. Every galaxy cluster, every burning sun, every planet, and every single atom inside your body is built entirely from that fragile asymmetrical scrap of leftover matter. Quantum field theory explicitly teaches us that the forces we feel and the particles we measure only exist because nature respects deep mathematical symmetries. But the undeniable reality of our own existence serves as living proof that at the highest energy scales of the early universe, those sacred symmetries must break. There must be an undiscovered phantom field or a completely unmapped quantum interaction that treats matter and antimatter differently. A hidden mechanism broke the rules just enough to allow reality to solidify, and the Standard Model, our absolute best map of the subatomic world, has absolutely no explanation for what it is. Faced with these monumental crises, the invisible grip of dark matter, the cataclysmic calculation of dark energy, and the rule-breaking asymmetry that allowed matter to exist, physicists have realized that the Standard Model has run its course. We have pushed the equations as far as they can go on paper. To find the phantom fields responsible for the missing 95% of our universe, we cannot just think harder. We have to strike the vacuum of space with a bigger hammer. This is precisely why the global physics community has established its absolute highest priority for the future of science: the planning of the Future Circular Collider, or the FCC. To understand why we need a machine of this scale, you have to look back at how we discovered the final piece of the Standard Model, the Higgs boson, back in 2012. To tear a Higgs boson out of the quiet vacuum, the Large Hadron Collider, LHC, at CERN had to smash protons together at 99.9999991%, the speed of light, generating billions of high-energy collisions every single second. Out of every 10 billion cataclysmic impacts, the fields aligned perfectly to produce just a single, fleeting Higgs excitation. The LHC is a technological marvel, an entry gate to the quantum world, spanning a ring 27 kilometers in circumference, buried deep beneath the border of France and Switzerland. But as powerful as the LHC is, it has hit a hard physical ceiling. It simply does not possess the raw kinetic energy required to probe the darkness any further. In the language of quantum field, theory fields reveal their hidden particles based on a mass and energy scales. If a phantom dark matter field or an antimatter breaking field exists, its corresponding particles are likely incredibly heavy. According to Einstein's E equals mc squared, creating a heavier particle requires a massive localized concentration of pure energy. If the energy of a collision is lower than the mass energy threshold of the particle you are trying to find, the probability of that field excitation appearing drops to absolute zero. The LHC cannot see these dark fields because it cannot hit the vacuum hard enough to make them ripple. The proposed Future Circular Collider changes the scale of the game entirely. The FCC is planned to be a colossal underground ring spanning nearly 100 kilometers in circumference, nearly 4 times larger than the LHC. It will operate at collision energies, reaching 100 tera-electron-volts, a power level 7 times greater than anything the LHC could ever dream of manifesting. By smashing particles together with this unprecedented, brutal force, physicists are planning to do 2 things. First, they want to create a literal Higgs factory. Because the Higgs field is responsible for giving mass to other particles, by resisting their motion, studying the Higgs boson with extreme precision is our best backdoor entry into the dark sector. If dark matter interacts with anything in our world, it is highly likely to couple slightly with the Higgs field. By producing millions of Higgs bosons and tracking their behaviors down to the smallest decimal point, the FCC can look for tiny anomalous energy leaks, moments where a Higgs boson decays into something our regular detectors cannot see, flagging the presence of a dark coupling. Second, the FCC is designed to hunt for the structural cracks in our current equations. When you run experiments at 100 tera-electron-volts, you are effectively using a high-powered microscope to peer into the finest fabric of space-time itself. At these extreme energy scales, the virtual particles running in the loop diagrams of our calculations will begin to change. If there are heavier, undiscovered fields active in the universe, their virtual excitations will feed into these high-energy interactions, altering the measurable outcomes in a way that our equations can finally detect. The infinities that once plagued Feynman and Schwinger will no longer be cleanly absorbed by standard renormalization. The theory will begin to fracture, showing us exactly where the new physics begins. Building the FCC is an enterprise that will take decades and cost tens of billions of dollars, pushing human engineering, superconducting magnets, and computing to their absolute limits. But it is a necessary price to pay. We are currently standing at a frontier where our best theory accounts for only 5% of reality. The FCC is not just a larger pipe for smashing atoms. It is a monumental searchlight designed to pierce the veil of the dark fields, forcing the missing 95% of the universe to finally step out of the shadows and reveal itself. What this grand extension of physics ultimately reveals is that the universe is far vaster and more mysterious than our senses or our current instruments could ever imply. The vacuum of space isn't an empty void. It is a hyper-complex, multi-layered fabric of quantum fields, all humming at their lowest possible energy state, overlaying one another in the exact same space. The world we see, touch, and experience, the entire 5% of reality mapped by the standard model, is nothing more than the visible crest of a massive, unseen quantum wave. You are not just a temporary arrangement of regular matter. You are an island of light floating on a dark, uncharted cosmic ocean. The realization that 95% of the universe is locked away in phantom fields is not a failure of modern science. It is an invitation. Just as Richard Feynman used simple diagrams to tame the terrifying infinities of early quantum mechanics, and just as Max Planck took a leap of desperation to introduce the quantum todays, physics stands at the precipice of another monumental revolution. The cracks in our equations regarding dark matter, dark energy, and the antimatter asymmetry are the historical signposts showing us where the next great breakthrough is waiting to be found. As we look toward giant leaps in engineering like the Future Circular Collider, we are preparing to venture directly into that darkness. We are learning to ask new questions, write new mathematics, and listen to the silent hum of the fields that refuse to speak the language of light. The fields we currently know are not the end of the story. They are merely the opening chapter, and the true map of Von Vaught is still out there waiting to be written in the dark.